Okay, so last time we actually introduced to you the visitor design pattern. Again, let's review what the problem is very quickly, and then we talk about visitor pattern in details for architecture and also for especially runtime. So the problem we are trying to solve in some way is very similar to the composite design pattern. So when you study for these two patterns, composite and the visitor, try to study them as a package. So composite is like a phase one, just for defining structure for recursive tree. And then for visitor is about to really add in as many operations as you wish for manipulating the tree. Okay, it's like phase one and phase two. And so this is the composite design pattern that we talk about for our particular small expression language. And it's actually a very practical problem because later on, if you want to build a compiler for your particular projects, that's kind of the structure you would need. Okay, I can point to you some reference maybe later in the course, so you can also study for your own benefits. Okay, so that's a motivating problem. And then we basically talk about the so-called open-close principle. Okay. But by the way, so we said that if you simply want to add in operations simply at the root of the hierarchy for the inheritance, it's going to violate single choice principle and also cohesion. Right? Review the last recording for why. And then we talk about violating of the two principles, and then open-close principle. Again, let me just mention very quickly verbally. Open-close principle simply means when your system got multiple parts, you have to, as a designer, commit to which part should be open and which part should be closed. The open part simply means every time if there's some extension you would like to add to your system, the open part will be the part to add, whereas the closed part should remain stable once it's defined. Of course, it might be that in practice, it may not be the case that you never touch the closed part. Maybe you have to touch it rarely, but not often. Okay. So now we talk about specifically for the visitor pattern. Oh, by the way, I kind of switched the alternative over here on the slides. You can see the updated version just to correspond more closely to my iPad notes. Okay, it's a minor change. You can download the latest slides. We talk about in order to satisfy open-close principle, if you think about the problem over here, right? Let me switch the iPad very quickly. Okay, so now this is basically the problem we are trying to solve, right? For our small expression language, which might be subject to change, either extending to the language structure or it can be extension to the operation. So we talk about structure over here. So the structure is basically the composite design pattern that we talk about, right? You can see so far we only support constant and also addition. So that's the structure part for the language. We also got another part which is called operations. Operation can be evaluate, pretty print, and also for type check, or even for code generation. You can add in as many as you like. So these are basically the two parts for our system, for our own application. So now, in order to satisfy open-close principle, we have to commit as to which part should be open and which part should be closed. And we talked about the two possibilities last time. Specifically, in order for visitor pattern to work, right? When we talk about the visitor pattern, so one thing to really understand, for the visitor pattern to work well, as we'll explain at the end of the lecture, we have to make sure alternative number two is the way to go, which means the structure of your language, once defined, should be rather stable. For example, maybe, of course, realistically, your language may not be as simple as just constant and addition. Maybe you want to make the grammar very similar to as rich as maybe iPhone or as rich as C#, etc. Right? Once you reach like a version 1 of your grammar, you should keep it stable for a while before you try to add more language elements to it, like a different version. Okay, so the structure part should be closed. On the other hand, the operation parts can be open. So this is really important. So this is where the visitor will actually shine, as we'll see. Okay, we're going to review the visitor architecture, and then we'll see how that works at the runtime. But now, number one things for you to remember. In order for visitor to actually work, you really have to know which part should be open and which part should be closed. Okay, so there's a very typical design decision you have to make. It must be the case that the structure must be closed and operation must be open. We'll explain why a little bit later. Okay, and then the next thing will be, okay, that's the architecture for our visitor pattern. Okay, let me just see if I miss anything from the slides. I believe everything has been talked about. And then, okay, so here I also updated the slide to emphasize, in order for visitor pattern to apply, you have to make sure alternative number 2 is really the design decision you have made. If for some reason you decided that alternative number 1 should be the case for your application, which means the structure of the language should be open. In that case, visitor pattern would not be applicable, would not be the way to go. Okay, we'll talk about this design decision at the end as a summary later. Okay, close and open, you can read it. It's already been talked about. Okay, so that's the architecture we want to review very quickly. Okay, let me just, I don't need to really review from scratch as we did it on Monday already. So let me just talk about the most important thing. So if you look at the visitor design pattern, number 1, you can see this part over here on the left-hand side. So this part here is really about, okay, let me just not to cover the accept. Okay, I mean here. So this part is really the composite design pattern, the structural part. On the other hand, you can think about this part over here is the operation. Okay, and then, so this is the operation. And in order for the visitor pattern to really work, in order to obey design principle, we will illustrate that in just a moment. Okay, for composite, it should be the closed part, which means whenever there's any extension for your system, it should not be to really extend, should not be to add a new structural element to your language. On the other hand, the operation part can be just open. Okay, that's the open-close principle, the particular alternative we're going to choose for a visitor. Okay, so that's number 1. Okay, we got open, we got closed. And now, for the composite part, you can see the only thing we are adding over here is called accept, right? You can see for the accept over here, for every expression, it's going to have a command called accept. And that one there is going to take a parameter of type visitor. And the visitor over here is the static type, right? For the visitor, which means at the runtime, visitor can be any of the descendant classes of the visitor. In which case, you can see dynamically, it could be evaluator, it could be pretty printer, it can also be type checker. Okay, just mention that quickly, right? So that means at the runtime, it could be either, okay, I'll just write it briefly. It could be evaluator, it could be pretty printer, it can also be type checker. Okay, so any one of them. Okay, hopefully so far it's clear to you. And then we're going to talk about exactly how you can define each of the accept over here. It's incredibly standard how you can implement the accept feature at the composite side. Okay, we'll see that. Okay, and then notice that over here we have 1 and also we have 2. Okay, so we have 2 effective descendants. And when I say effective, I mean classes that's not deferred, which means classes that's fully implemented. Okay, so the 2 here is a very important number. Okay, so now if you look at the visitor part, you can see here we got at the top level we got a visitor class which is deferred. Okay, and then the number of visit feature over here we have corresponds to how many effective descendants we have. In this case, we have 1, which is called visit constants, another one, which is called visit addition. So it really depends on how many you need. So now let's say in this particular change, which shouldn't be the case, right? Because we talk about open-close principle. If one day I really decided to actually add a new class over here, for example, I'll just make a simple case just for now. If I want to add just another class over here, let's say, let's call that also effective, let's say Boolean constant over here. Let's say if I do that, right? So now in that case, that would mean I just need to add another visit Boolean constant feature over here. Of course, the parameter will just be whatever type it should be, right? So now in this case, it will be maybe a constant, and then it will be Boolean constant. Okay, hopefully so far so good. Okay, and then under visitor, the root, we can define as many descendant classes as we like. Okay, so now you can see for evaluator over here, and for pretty printer, and also for type checker. For each one of them, they have different purposes. That's why they have to be separate into different classes for the purpose of cohesion, right? So remember, cohesion here is actually satisfied because evaluator has only served to do evaluation, and pretty printer only served to do for pretty printing and etc. Okay, so now if you look at this, let me just make it more obvious to you. If you look at this particular visit constant here, you can see visit constant comes from the superclass over here. And also you got another visit constant over here. And also you got another visit constant here, right? So now you can see it's quite obvious we got 3 visit constant over here, right? This is number 1, this is number 2, and this is number 3. We got 3 versions of visit constant over here. Are they the same? Apparently they are not the same because they serve different purposes, right? So now either 1 or 2 or 3. So which version to call at the runtime depends on the dynamic type. Okay, dynamic type over here because we talk about runtime behavior. Depends on the dynamic type of the visitor. Okay, just keep that in mind. Okay, and similarly for visit addition, and visit addition over here, which version should be called at the runtime also depends on the dynamic type of the visitor, right? It really depends on which dynamic type of the visitor we have created. Okay, and for you as the implementer for the visitor package for cluster, in that case, the way you implement visit constant over here would be different from how you implement the visit constant here, right? For example, if you say visit constant over here, and then you simply got some constant object, for example, right? Let's say if the dynamic type happens to be evaluator, you may just evaluate to the value of 2, right? It's an integer value. On the other hand, here, if you say visit constant for pretty printer, you might simply print out the string value 2, right? And also for visit constant over here, for the purpose of type checking, you're basically asking whether the value 2 is actually type correct. In that case, it's simply just type correct because the number by itself has nothing wrong about its value usage. So now over here, if you say visit constant over here, and then you want to say for the value 2, it will just be true. Okay, so now let me mention one more thing. Of course, exactly how you actually implement the individual descendant classes for the visitor is completely up to you. But I want to give you some general guidance, okay? And then I will highlight it here right away. You can see in the case of evaluator, you're going to, after visiting your tree for the expression, you're going to have some evaluation result, which will be, in this case, integer, right? For example, 2. If you're talking about pretty printer, in that case, you're trying to just print out a string without evaluating it. In that case, it will just give you the value 2. And then if you want to do type checker, in that case, it will actually just tell you either it's type correct or not, right? Okay, so any questions so far? Before I make a mini conclusion. Okay, so now let me write down what you should really do as a general guidance for your visitor pattern. And that actually has to do with the question I asked you about last time. Okay, let me write it down here. Okay, so what I'll write to here is over here. For each descendants of visitor. For each descendants of visitor. The value, the return value, may be of different type. For example, in the case of evaluator, you'll get integer. In the case of pretty printer, you get simply a string. In the case of type checker, you will get a true. So now, it now comes to another design decision. So now, let's say if we have, for every visitor, we want to have to say after visiting the whole expression tree, I want to get some result. So now what should be the result type, right? One design decision could be, if I simply try to say in the visitor class, the top class, I will simply say value over here, but now I want to have a type. that's going to be accommodating enough for integer, for string, and also for Boolean? Is there such a type in an OOP language? That's my question. Anybody? Or put it another way, is there a common ancestor class in the inheritance hierarchy for integer, for string, and also for Boolean? Any? Yes, thank you, Ken. So now it will just be any. So one way to really implement your visitor pattern is to say value and then you say any over here. You simply put it at the top level. So that means every descendant class for your visitor is going to have this value of type any. However, is this really a good design? That's another question, right? I will argue that this may not be a very good design for the following reason. If I'll just mention very quickly, right? So now thinking this way, right? Let's say we follow this particular design decision. So value of type any is defined in the visitor class, let's say, okay? So now, in the case of the pretty printer, let's say pretty printer, let me put it here, right? And now, let's say if I have a client of the pretty printer, right? Pretty printer over here. How are they supposed to retrieve the value, right? So now, if you try to say, if I got some pretty printer object, let's assume PP was declared to be pretty printer, right? The pretty printer. Okay, so now if I say PP, the value over here, okay, let's say I want, given that the return result value for pretty printer should be of type string, I should be able to do some further manipulation on the string, right? So now, if I say pp dot value dot, for example, append, I can append something to the end of the result if I wish. So now, if I say pp dot value dot append, I want to append maybe, for example, I want to append a period after the result. Okay. So now, here's my question for you: is this line going to compile? Anybody? Let me make my question very quick. Okay. Good. Well, Ken already got a right answer. I heard yes. I also heard no. Okay. Let's see. Let me just tell my question again, and then I'll tell you the answer right away. Okay. The question goes like this. The original motivating question is like this. For every descendant class of the visitor, we know that its returning result value could be of different type. For evaluator, it will just be integer because every expression we are calculating is integer expression. For pretty printer, the return value should be string because we just want to print out some string value, string literal. And also for type checker, all we want to know is whether or not it's type checking. So that should be true or false, right? It's a different type. So one way to design this would be at a common ancestor for all the visitor classes, I'm going to define value of type any, right? So that means this particular attribute will be inherited to here, and also inherited to here. So now, let's say this. If I declare pp of type pretty printer, which is this particular class, I am expecting this return value to be of type string, like a string literal. But now, when I say pp.value.append, can I do that or not? Okay, so hopefully now, once I clarify the question, apparently it wouldn't compile for the following reason, right? That's something very important for you to know, right? So now this particular part, pp.value over here, has the static type any, because this value any is simply inherited to over here. So now, does the any class support append? No, it doesn't. Okay, so now, this will not compile. In order to make this compile, what should you do? You should do a cast. So a cast will go something like, I'll write it down very quickly, right? You're gonna say check attached, and then of course you will say string. I'll say st for short. Okay, string, and then after this you have to say pp dot value, right? And then you might say s string value, and then right. Sorry, just running out of space, but you can see I'm just trying to do this the cast syntax. And then once you get this sv over here, so that one there is of static type string, right? And then you can use sv under the cast, and that's the end of the cast. Okay, it's a little bit clouded, but hopefully you can see the line of thoughts over here. Okay, So now that tells us if you want to define the value for every individual visitor, it's not a good design decision to simply put the value as of type any at the top of the hierarchy. That's a conclusion. Okay, so you will rather put individually. Let's say you'll put in the evaluator class, you'll put value of type integer, and then over here for pretty printer, right? You will actually put value of type string, and also similarly for type checker, you will say value is of type Boolean. This may be a better decision, okay, but it will be more like a balance you want to actually do. Okay, let's now, I basically said everything I want to say about the architecture, but at least you can see how classes, what are the classes that's available for us to pay attention to. So what I want to do now is to go over to see how the visitor pattern will work. Okay, so this is something we talked about last time on Monday. So now these 3 lines are to build a tree, right? I will do some exercise together with you quickly in just a moment. Okay, and then the way you use the visitor pattern is to say add over here is simply of type expression, right? And now expression itself supports the accept, right? Just make it bigger for you. You can see for the expression class, you got the accept. Okay, so now you can simply say add the accept, and then you use some v over here, and the v here dynamically is evaluator. So that will guarantee later on when you actually call the visitor, is going to call the correct version, right? You can see because dynamic type is actually evaluator, so later on you will be guaranteed to call only the versions of the visit commands in the evaluator, right? It's a very informal sketch quickly, and then we'll get to the precise detail. So now comes to the last point before I move to tracing. This is the part of the code I want you to think about, right, over here, right? So now hopefully now with the context I just explained. So now let's say I don't have this particular cast, okay? Apparently this cast is to make sure if you actually got v over here as an evaluator, in which case, yes, indeed. So that's why we can cast it to evaluator. And then we say eval the value equals 3. So that means eval the value is of type integer, right? So that tells us we are referring to this particular value over here, right? So in the evaluator class, we assume we got value of type integer. So this is why we need such cast. So the question I posed to you at the end of Monday was like this. Alternatively, let me write it here. Alternatively, let's say if I simply say v, which is a visitor, okay, dot value equals 3. Okay, it's also a very common mistake you might make for the visitor pattern. Now, if I simply say v dot value equals 3, is this going to work? Very quickly. Okay, in order to decide whether this will work or not, is you have to see what's the type on the context object, right? So now again, very quickly. So now if you try to see v over here is a context objects. So if you look at that, v, what's the static type? V was declared to be visitor. So in that case, you actually have to say, so the static type would just be visitor. Okay, so now does visitor v support value? In our second design, the better design, no, it's not there because value belongs to individual evaluator or pretty printer or type checker. Okay, so that's why this will not compile because value is declare, sorry, I'm just saying here, just different color, hopefully you can see. So it's declared at the individual visitor descendants. So you have to use proper casting for that. Okay. Okay, guys, any questions for what I talked about so far? Okay, so far it's a little bit review from last time, but also I try to add more information to you. But the most important message for you to see is like this. individually for every descendants of the visitor, you have to support like a value of the appropriate type, right? Okay, that's something you want to keep in mind when you do the evaluation. Can we use method overloading in the visitor? Okay, so for IFO, okay, it's a design decision for the language. There is no method overloading for IFO, so you cannot do it. But if you go back to some C family language like a C# or Java, they do support overriding. Okay. So for example, in Java, okay, in IFO, it does not support overloading, right? No feature overloading. Okay, in that case, you have to say, for example, visit constants. And also you have to say visit, for example, addition. And then the constant will just take a constant, right? And addition will just take an addition. Okay, again, it's a design decision for the language. Okay, let's say in Java. In Java, you can feel free to also use this one here. That's not a problem. Okay, in Java, either you can say version 1, you can say visit constant, and then you simply take constant. And with a different method, you can say visit addition. And then over here, you also say addition. Okay, I'm just mimicking how you would do it in IFO, right? In Java, you can definitely do it, not a problem. However, Java also supports method overloading. Okay, it also supports method overloading. So now in this case, you can also do version number 2. And in this case, you can simply say visit and also visit. You can have 2 methods with the same name. You'll be allowed as long as their types can distinguish between them. So now in this case, you can say visit, and then here you can say constant, maybe C. And then here you can say addition, and then maybe say A. Okay, so just a quick comparison between the 2 languages. There was another question about what's the difference, very quickly. Okay, that's just an aside. What's the difference between check attached versus if attached? Okay, I would suggest you refer to the recording back to maybe right after the reading week when we reviewed the inheritance. When I talk about casting, I did talk about the difference between these 2. Okay, I would suggest you review them. Okay, so we don't have to spend time over here. Okay, so now let's try to go further about how the visitor pattern will work at the runtime, right? Now we really get to the critical part. But before that, let's do a very quick exercise together, okay? So now, let's say we are trying to build a tree over here, right? This is from line number 4 to line number 6, right? How can you visualize the structure over here for building a tree, right? That's something I would like to show you very quickly, okay? So now, the way we build a tree is very similar to how we build a tree for manufacturing, for the computers, right? In the composite design pattern. But let's see how we can do it. Let's see this. For line number 4, okay, line number 4 over here, when you do it, you're simply creating one constant called C1, right? So C1 is pointing to some constant over here. I'll say C for constant. And C2 is just pointing to another constant. So C2 is just pointing to another constant. I think visualizing the object structure is very important because when we trace how the visitor is going to visit the tree of the objects, it's going to be important to visualize that. Okay, C1 and C2, and then you can see for C1, 1, and for C2, the value should be 2, right? So there's a value attribute over here, let's say, and then one will be 1, the other one will be 2. Okay, that's line number 4. And then let's do line number 5. Line number 5 over here, we just try to create an addition over here, right? That one's simple. You just say add, and then add is now going to point to some addition objects, and then what attributes do we have? You can see from the diagram over here, we got left and we got right on the every composite, including addition. So now in this case, is now going to be the left and also the right. Okay, so now I'm just going to point. So now when you say the make, let's assume C1 is not going to left, C2 is not going to right, right? So left is going to here, and the right is going to here. Okay, so that's the tree we are building, right? So it should be very familiar to you when you did the tree operation back in 2011, okay, in the previous data structure course. And then finally, so the tree building is done. So now we have to think about for line number 6 over here. So when you create this particular evaluator, so what you're doing is V is now pointing to some visitor objects. Dynamically, it's going to be evaluator. So now it's going to be eval, okay, something like that. And then for the evaluator, remember from the previous one, we said for evaluator, we assume you have an attribute over here called value of type integer. So now what we will have is the value is of type integer. So it's unknown just for now. But somehow we're going to see exactly how these two, this object here for the visitor and this tree over here for the composite, how they work together bidirectionally, right? That's something we're going to see at the runtime. Okay, we'll go to that detail in just a moment. Okay, before that, I would like to just go over maybe some slides to show you a little bit of code, so you have some idea how the code structure looks like, and then we'll trace them in detail. Okay, so there's a visitor slides over here, and then let's go for the composite part, right? Just the expression, right? We'll talk about accept feature over there, and then let's say for example constant, right? So now the first one we see very quickly is about the constant. You can see the constant is basically over here. So this is a class that we're talking about over here. For constant, you simply say accept, and the way we implement each accept is very standard. The way you implement it, simply say we are going to let V over here, the parameter, call the current expression objects. But which feature should we call, for example, right? So now, since we are now in the context of the constant class, so that means we should really say v dot visit constant. So this is why we said the rule is for every descendant class for the composite, you must have the corresponding feature. For example, visit constant and also visit addition, right? Which version will actually be called either here or here or here, depends on the dynamic type for the visitor. Okay, that's something we'll see. Okay, let me go back here. So now that's why you will simply say v.visit constant and current. So now this one-line implementation applies for every effective descendant class for your composite, either for the base case or for the recursive case. They apply to all of them. Okay, and then I'll just want to show you another one. This one I can let you tell me how it should be implemented, right? So now if you have the class addition, so now we are talking about this particular class, right? It's a composite class over here, addition, and it has the accept feature. So now, can you tell me how it would be implemented for the accept? You can see the signature is also visitor. But now, what should be that one-line implementation? Oh, by the way, for the previous one, you can see the parameter over here. Oh, let me show you one more thing. Okay, you can see for visit constant over here, you can see for visit constant, its parameter is simply constant. So now we need to pass a variable over there. And also for visit addition, the parameter type is addition. So it depends on which class you are in, right? So that is why over here, when you say you want to define visit constant over here, you simply pass the current objects. So this might require a little bit of thinking, but I would suggest we'll delay that explanation in a little bit later. But the current here is going to allow you for bidirectional communication between the visitor and the composite. We'll see exactly how that's going to happen, right? But current is of type constant over here, right? Current is of type constant, and constant will simply satisfy the constant over here, like one I'm pointing to in the arrow, the constant here. So now a question for you. How do we implement this particular accept feature in addition? How do we do that? What should be the one line we do? Yeah, think you can. So that's exactly right. So you will simply do v.visit addition, exactly, right? So now, for example, if under addition over here, if you simply say v.visit constant, for example, and then say current, the compiler is not going to be happy because visit constant is expecting some constant. But in the context of addition, the current is of type addition, so they wouldn't match. Okay? So the one-line implementation is very standard and simple. As you actually get more experience about this particular pattern, you may simply just memorize it, right? That's quite natural. But it's really important to see later, as we explain in detail, why we should simply just put current over here. So there's a very important reason for that. Okay, well, we'll get there later. So guys, any questions about how to define the visit? How to define the accept feature? Any questions? Okay, we haven't got to the tricky part yet. Of course, the tricky part really is when everything works together. But now I just want to tell you individually how class can be defined. Any questions? Okay, so now let's go to the other side. So now we talk about basically this side of the classes, right? This side. So let's say now we talk about this side over here. Okay, so let's just talk about maybe just evaluator, for example, right? Let's talk about evaluator and see how we can define the two visit constant and also visit addition. Let's say how we can evaluate these expressions, and then we'll do one example. Okay, so now for each descending class for expression, we're gonna have visit. Okay, that's the rule I talked about before. Okay, and then let's say visitor. That's a deferred class, right? So now this class is the top level over here, the top level. And then we have visit constant, and also we got visit addition, right? We covered that already. Let's say for the evaluator, that one there, evaluator actually inherits from visitor. So that means every deferred feature in the visitor, namely visit constant and visit addition, they must be implemented in the evaluator, right? So now how do we implement them? So let's say value over here, you can see the value here is the visitor specific value, right? In the context of evaluator, we make the type of value integer. But now later, if you want to implement, let's say pretty printer, in that case, you might declare another value here of type string, even though they're both code value, but they have nothing to do with each other, right? They're independent. And then we got visit constant over here. Okay, so now for every visit command in a particular visitor descendant class, you have to do something specific to that purpose. In this case, we want to do evaluation. How do you evaluate a constant? That would be the easiest case, right? How do you evaluate the constant 5? Well, just 5. How do you evaluate 10? Well, just 10. So what you would say is, you would simply say, when I want to visit constant from evaluator, I'll say set the value over here to be c.value. The c here is the constant. Whatever the constant value is going to be the result for the evaluation, if that's what you want to evaluate. You can think about visit constant is like the base case for the recursion. As we'll try to trace the code at the runtime for visitor, you can think about everything work together like a recursion. Okay, and the termination case for the recursion, like a base case, would be when you reached the constant. Okay, and then we got also visit addition. So now, how do you define this, right? Before I try to, well, we'll trace the code in just a moment, right? Before I try to show you the code, right? Conceptually, the code is very easy. Okay, let me just give you a little bit of hints over here. Okay, let me switch to my iPad and then I will show you. Let's say this. Let's say how we can evaluate addition. I would say if you simply got 1 plus 2, that's very easy, right? You simply evaluate 1, which will give you 1. Evaluate 2, that will give you 2. And then add them up together, right? That's a very simple case. But I'm pretty sure after your learning from 2011, you have to do such operation recursively. So what do I mean? Think about conceptually, right? It's a tree. The root of the tree tells you it's an addition. And then the left child and right child, they are simply of type. Let me just remind you. The type for every composite is simply just expression. So that means they can be arbitrarily complicated, something like this. It could be something like, maybe there'll be 1 plus 2 plus 3 plus 4, for example, right? I know we don't have the parentheses in the grammar, but I just want to illustrate. If I want to evaluate this particular addition, how do I do that? Well, I cannot necessarily evaluate the left-hand side right away, so I have to recursively evaluate that. And when I recursively evaluate that, I will see that it's just another plus. And then recursively evaluate 1 and also 2. And for them, they're the base cases. You will return their value right away. And similarly, when I recursively evaluate 3 plus 4, it's too complicated for me to evaluate, so I will try to recursively evaluate this plus over here, which will in turn call evaluate 3, evaluate 4. In that case, I got the base cases, right? So now, here's the idea. Okay, so now let's think about it, right? So now, if I got the left, let me try to, the left can be arbitrarily complicated, right? Let's say, let me just make one more, okay? Let's say addition, so let's say add is the variable. You will see that in the example code as well. Add is the variable name that points to the addition expression tree, right? That's the root of the tree. So this part is add dot left, which can be arbitrarily complicated, for example, 1 plus 2, or even more complicated than that. And then we got another one here, that's over here. So this one here is add dot right, right? So now, how do we actually evaluate this, right? So thinking this way. In this case, if I have some evaluator, let's say evaluator, I'll say eval, right? Evaluator. If I got eval of type evaluator, so first of all, what I'm trying to do is, I'm trying to say eval over here, because I know at the top level is simply just plus, it's addition. So I would say eval dot visit addition. And then I will simply say add over here, right? So I'll put add over here. So you will see it's the same objects. Okay, so now I want you to take a quick, careful look of this particular feature call. Eval of type evaluator is calling visit addition, and then the parameter argument I'm passing is the add, which is the top of the expression tree. Okay, so now can you imagine how do we evaluate recursively? Okay, before I give you the answer. Okay, or I give you a little bit hints over here. Can we reuse eval? Okay, you can see eval over here. Can we reuse eval to, you know what? Let me not to give you too many implementation hints. Okay, you know what? That's something that's your implementation freedom. I don't want to intervene. Okay, let me put it this way. Okay, how do we evaluate left and also right recursively, and then combine their result? And in this case, the way we combine them is using the plus. Okay, that's my question for you. Okay, okay, for those of you who got clear answer, you can feel free to type to me. But if you got a question about what I'm asking, so please feel free. Okay, and then I'm gonna give you the answer. So I think clarifying this at a conceptual level will help you once you see the code, right? Because typically when I show student the code right away, they might get some confusion. So I thought might be nice to clarify conceptually first of all. Aha, so I from somebody, so use an evaluator to evaluate the left, and another evaluator to evaluate the right and add a value. Exactly right. Exactly right. Thank you. Okay, so now let me tell you what we should do. Okay, thinking this way. What you should do conceptually goes like this. For cleanness, I would suggest try not to reuse the same evaluator objects to evaluate both the left tree and the right tree. Of course, it's doable programmatically to make sure you store the intermediate result carefully. But I would say for cleanness, it's better to create local variables. Okay, so what I would say is like this. To do this conceptually, what you would do is like this. You would say, let's say eval left, okay, and also eval right, okay, and then they are of type evaluator. Okay, so now basically I'm going to use eval left for evaluating the left. I'm going to use eval right to evaluate the right. Okay, so now I need your help. Conceptually, we are okay to know that we're going to use this particular evaluator to evaluate the left, use this particular one to evaluate the right. But how exactly do we call that? Let me tell you something first of all. If I simply say, okay, I'm going to write something that's wrong, but it's good to know why it is wrong. Let's assume that I already say creates evaluate left dot make, and also I say create evaluate dot right dot make. Let's say I do that already, right? Let's not let it distract us. What I want to ask you about why it is wrong is like this. If I simply write eval left dot visit over here, for example, addition, and then I'm running out of space, I'll simply say argument here, I'll just say at dot left. So my intention is after this line, I can simply say eval left dot value should really give to me the evaluation result. Okay? So now guys, question for you. It's really important. I want you to look at this line over here. Is this correct? Okay, for those of you who actually got the slides with you, please take a look at the architecture and or even the source code I gave to you. Okay? Okay, I see no. Okay. Okay, I see another question here. Okay, apparently you guys can realize this is actually wrong. First of all, let's see why it is wrong. And then one of you actually suggested something nice. Let me do that, okay? First of all, this is not going to compile. Okay? This is not going to compile because when you say visit addition over here, right? So now let me go back. If you go back to the architectural diagram over here, visit addition, right? Visit addition will take only addition type, right? And not expression type. In that case, what we will have is this. What it is expecting is going to expect addition. However, at the left may not be exactly addition. For example, if you simply got add over here, but the left is simply just constant, in that case, it wouldn't compile, right? Okay, just get it right. And guys, any question about this? Okay, maybe rethink about this. Okay, this will not compile. Simply because at the left, the static type is simply just expression. And visit addition over here statically is expecting addition. And now expression is not a descending class of addition, right? That's why we review. When we review the inheritance, we talk about the feature arguments, polymorphism. Well, I think now is the time for you to review that part. That's why we review that part explicitly. Okay, so this will not compile. Okay, please review. Make sure you understand this. So now, how can we solve it? Okay. Okay, so now what we want to do now is how can we resolve it? Okay, let me just tell you the answer right away. Otherwise, we're dragging too long. Okay, the way to solve this is by this. Okay, simply say rather than using eval left as the context object, that's what you would do. Remember, for every I know many of you have some suggestion or question. Let me review them in just a moment. Okay. So now remember in the expression class over here we got accept. So this is something very nice for us to use. So now that's something you want to get used to yourself. When you want to evaluate some expression there, rather than having the visitor dot something, most likely you can simply use expression dot accept. Okay, That's something you want to get used to. Okay, that's exactly what we're going to do. So what I would say here is, in order to evaluate this, I'll simply say add dot left, which is of type expression, dot accept. And then let's accept eval left. That's one side. And then let me put another side here. Another side would be add dot right dot accept. And then eval right. So after the two acceptance calls, so after this, what you will get, so after these two, you can combine the values together. So now after these two are already on the top, right? So there's a sequence there. After these two, you can simply say eval left dot value, which is the evaluation result for this particular tree, and then plus, over here you can say eval right dot value. That's going to be the result for the right tree. Okay, let me take a look at your questions there. Maybe some of them have been addressed already. Okay, very good. Okay, so I think most of the questions are addressed already, and some of them about the dynamic type for the visitor, that's something we'll get into when we trace the code. We're going to do it just right now. Okay, so I would say I spent a time sketching this particular page for the reason that it's really important for you to know about how to handle recursion, especially when your expression has recursive structure. We call left subtree, right subtree. Or in general, the subtree can be arbitrary number, like a B tree in general. In that case, what you want to do is for each individual subtree, use a separate local variable for the visitor of the correct type, and then try to accept them one by one, and then combine the result together for the local visitors. Okay, that's my main point. Okay, so now with this understood, if I go back to my slides over here, now you will understand why we're doing exactly what we did. Okay, you can see eval left, eval right. And then we got a dot left accept, right? So now you see exactly why. And so also a dot right accept, and then value is assigned to eval left and then eval right. Okay, over here. Okay, so now I have already seen, we have already seen the code from both cluster. Okay, we have seen the code from this part here, and also the code from this part here. So now the final part for the visitor pattern is to trace it. Okay, let's trace it now very quickly. Okay, so now this is the test method I want to trace together with you, and that's exactly the same as before. Okay, and again, we got add C1, C2. And we talked about already how you can build a tree, right? That part has been done. And then we'll simply say add.accept. The add over here, you can think about in general, the add can just be as complicated as, at the add over here at the top, which got left subtree and also right subtree, right? In general. And then after that, we simply just want to retrieve the value from the evaluator, right? Where we mentioned that it should be a cast. Okay, so now let's try to trace this particular simple structure. Even for that, it requires quite a bit of detailed explanation. Okay, so now let's do it. So now that's the most important part for, well, every part is important, but this is kind of what usually when people talk about the visitor pattern, they will talk about a word, a buzzword called double dispatch. Okay, double dispatch. And you can think about double means 2 times, right? Double means something is going to happen 2 times. And dispatch over here specifically talk about dynamic binding. Dynamic binding. Which means somehow when I try to use the visitor pattern, just a single line of usage is going to trigger 2 occurrences of dynamic binding. So that's something we want to see. Okay, let's just see this diagram very quickly. So we got our evaluator, exactly how I drew it before, right? Just a little bit better layout. We got evaluator whose value is simply unknown for the moment. We got a simple expression tree. We got add over here. The left subtree is over here, which is just a constant. The right subtree is over here, which is also another constant, right? So we got the addition at the top level. And now what we want to trace is add.accept. Okay, let me write it down again. So when I say add dot accept and v, so you got every definition over here. So now we want to see exactly how double dispatch is going to occur. Okay, and now also what I mentioned, what is called a callback by passing the current will also happen over here. Okay, so now let's pay attention to this tracing here. Okay, now if I want to call this particular feature call or method call, how exactly is the first dynamic binding is going to occur? Okay, so this is the first dispatch. Okay, anybody try to explain to me, okay? Try to explain to me how exactly the first dynamic binding is going to occur when I try to execute the feature add.accept v. Okay, if you don't like typing, if you want to speak up, please just let me know on the chat. I can unmute you if you wish. Otherwise, you can just type. That's fine. I just want you to think about before I tell you the answer. If you only look at this method call, okay, I'll wait a little bit. Okay, pretty good. So I got two responses. They're both correct. Thank you, Ken. Thank you, Minesh. So the first dispatch goes like this. Okay, this is the context objects, right? Because dynamic type of add is add over here. If you look at the previous code, okay, add was declared to be expression. That's a static type. However, dynamically, add was created as addition. So that's a dynamic type. Okay, the same block of code is addition. Okay, can I just make the writing a little bit smaller? So give me one moment. Let me adjust it quickly. Okay, because dynamic type of add is addition. So we know that the corresponding accept command will be called depending on its dynamic type. So we know that the accept in addition. So now you can see addition is over here. And then we're going to call this particular accept, this particular version, right? So now in this case, this is the first dispatch. Okay, that's the first dispatch. Okay, in addition is call. Okay, that's my first question. Hopefully every one of you does not have much trouble. Okay, so now let me go a little bit further. After this, it would be very important for you to know exactly how the execution is going to go. We know that after the first dispatch, we're going to call this particular accept, and now we're going to call this particular feature, right? So now in this particular instance over here, v over here is the v over here. Agree? Okay. So the v, you can think about the v here is the v here, and the v here. Let me give you a little bit of hints. The v here, its dynamic type is evaluator, right? Dynamic type is evaluator. Okay, let me just tell you that. Okay, and then we are going to execute this particular line. Okay, and then we're going to execute over here v, which is evaluator dot visit. I'll say add just to save some space. So now, what exactly is this over here? You can see the current over here is simply just the keyword to refer to the current class or the current objects. But now, at the runtime, what exactly should this be? That's my question for you. Guys, any idea? So you can see every detail over here is very important, right? It really examines your understanding about OO. So I would suggest if there's any part here you're not too sure about, you really should review about your OO or inheritance. Let me make my question again. We know that after the first dispatch, we're going to call V the visit addition, right? That's what I'm writing over here, V the visit addition. Now, what would this current be? Okay. What would this be? What would this current? What's the expression over here? It's a single variable. Current would be of type addition. I agree with you, but what's the current? Yes, current. Okay, I think yeah, I think you guys are on the right track. Okay, maybe my question wasn't clear enough. I was simply asking what variable will be put over here as a current. Add. Very good. Very good. Okay, because now let's see why. Very easy. Because we're calling this particular accept, right? So now the accept is now having this version here, and now the context object is add. So that's why current over here will just be replaced by add. So current is like a this in Java. Okay. Okay. So I'm pretty sure. Oh, sorry. Maybe that's why it's good to be recorded, so you can also review this part here if you're not too sure. So now I'll simply put add. Okay. So the add is referring to this particular add object over here, right? That's basically the context object here. Okay. Okay. So now after this, what I will do is I'm going to talk about second dispatch. Okay. So now we're going to execute that. So now let me just talk about the second dispatch. So let me put it aside here. Okay. So now second dispatch. Okay, second dispatch. So now we want to say we're going to execute v dot visit addition, and then add. So now this will be where the second dynamic binding is going to occur. Okay, can anybody tell me how the second dynamic binding is going to occur? Anybody? Quickly. Okay, in a very similar way. Okay, very good. Okay, actually everyone, those of you who responded, you got exactly right. Again, thank you. So now, basically what's going to happen is this. Again, the context object is here, V. Depending on its dynamic type, we're going to call the corresponding version for visit addition, right? So now apparently we got only two choices. Either visit addition over here, or it can be visit addition over here. But which version should it be, right? So now you can see in the case of the, well, actually over here, I didn't show you the visit addition for other visitors. So now I already told you the answer. But if you look at the architecture, okay, either visit addition from evaluator, or visit addition from pretty printer, or visit addition from type checker. Basically, that's a question. Which version, right? Okay. So now, according to dynamic binding, I can write it down for you, just for preciseness. Okay. So now what we want to say is because dynamic type of V. Okay. You can see V is dynamically pointing to evaluator. Is evaluator. So the visit addition in evaluator is call. Okay, so this is the second dispatch, right? Hopefully you can see that, right? So that means we are calling this particular visit addition over here, right? And then it's simply just going to take addition, and this add is going to replace the argument over here, add. So now you can think about every occurrence of A here, it will just be add, right? And add over here. Okay, I'm not going to trace further, but I want to give you some exercise to think about. Two things to mention before I can take some questions for you. Okay, number one, the way we are trying to lay out this particular three lines correspond to exactly how I explained the subtree recursive calculation is before, right? Point number one. You can review that. Okay, number one. Number two, exercise for you. Okay. You can see over here, add dot left dot accept, and then eval left is one call for the accept, right? And also we got another one here. Let's say purple. Add the right the accept. There's another call to the accept. Each one of them, the green and the purple, each one of them got another instance of double dispatch. Okay, you see what I mean? Okay, so now I want you to do the following exercises. I think that's quite important in order to double check if you really understand double dispatch for a visitor. Exercises. Okay, explain double dispatch for the green one. The green one is referring to this line over here, right? And also another exercise is explain the double dispatch for the purple, which is add the right, the accept eval right. Okay, that's the purple. Each one of them just tell you another pair of double dispatch, another occurrence of double dispatch. Okay. All right, you can see it's quite a bit of details to really set up the tracing for the visitor. But usually people might find it not so straightforward when you first see it. But hopefully with some detailed explanation, you can also watch the recording later. Hopefully that's fine. Okay, guys, any questions? Okay. I got another question here. I'll try to answer to you offline. Okay, that one will require a little bit of distraction for the current lecture. Okay. Okay, since everybody's okay, so now I would like to point out two references to you. Okay, before we end the current visitor lecture, and then we'll go on to talk a little bit about observer. Okay, we'll do that. Okay, so now I believe that's all about the, actually for visitor, that's actually quite important. Okay, before I end it and give you future references. So now we can go back to revisit the visitor pattern and see why it's going to satisfy open close principle and also single choice principle, especially single choice principle, right? Let's see why. I got two illustrations over here to really help you understand how you can make a design decision. Again, for visitor pattern, we assume that this part should be closed. And this part over here should be open, right? I got another similar diagram. Okay, so this part should be closed. And this part here should be open, right? We got close open and close open. So now what we want to do now is like this. Let me just help you with the question. Let's say if a new language construct is added, let's say multiplication or something, right? If we want to really try to, a new language construct is added, so it's going to be added to the close part. Okay, apparently this tells us there is something wrong, because if you already claim the language structure should be the close part, then you shouldn't really modify that often. If you do this very often, then that's not good. But let's just see why it would be considered as a bad practice if you do this such change often. If let's say you would try to add a new language construct, let's say multiplication. Okay, multiplication. So what you will do is you're going to add a new class over here called multiplication. Multiplication over here is going to add a new class over here and a new class over here, right? If this is the only change you have to make, it would be okay. Okay? Okay, and also the second question is, if the visitor pattern is adopted, what should be what should be closed, right? It turns out what should be closed would be the language structure. So you can think about this particular slide is trying to illustrate to you why the language structure should not be modified often, because the consequence would be you're going to violate some design principle very badly. Okay? So now, go back to the original question. So now, let's say this. If I want to add multiplication, as I demonstrated over here, is this the only place I have to add to my design? When I talk about the whole visitor design, is there anywhere else I have to modify? That's my question. Will there be any other classes I need to modify? Or this is the only class I need to add? That's the question. Or should I touch the visitor side? Yeah, so that's good. So you need to modify the visitor classes, but now and each of its descendants exactly, right? Because now, since actually I already also gave you a little bit of warm up in the very beginning of the lecture, if you noticed that. So now if we add a multiplication, so that means over here we're going to say visit multiplication. And then here will be n multiplication. Okay, that'll be deferred. And then not only that, this particular command must be implemented for every descendant class over here, which means visit multiplication should be effective over here, should be implemented for evaluation. Also, visit multiplication should also be implemented for pretty printing. And also, visit multiplication should also be implemented for type checking, right? So now, what principle are we violating? I hope that's quite obvious to you. Okay? Can everybody see it's single choice principle, right? So this violates single choice principle. Okay, I hope that that's obvious to you. So now the conclusion is, if you're going to apply the visitor pattern, in which case you got composite, you also got a visitor, right, over here. In that case, the language part should be closed, because if it was not closed, for every new class you're trying to add into the closed part, it will involve, in addition to the visitor class, and also every of its descendant classes. So that will actually violate single choice principle, right? What if we do another kind of change, which is to change the operation? Are we going to violate single choice principle? I can tell you the answer. The answer is no. Let's see why. Let's say we are talking about two possible design changes. The previous one is considered as a bad change because the language part should be closed. But now, let's say if we want to add a new language operation, for example, let's say we want to add, let's say, code generation. Let's say code generation. So now where should we touch? Well, do we have to touch expression language? No, in this case we don't, because this package over here is only about structure, but now we are trying to add a new operation. So the only place we have to modify is adding a new subclass over here and call that, for example, code generation. And then, because that class, for sure, it must be effective in order to be instantiated at a runtime. But now, for every feature that's corresponding to the language element, which is supposed to be stable, we have to implement them, right? So now that means in a single place, we have to say visit constant and also visit addition. And every one of them should be effective. You can see this is a single place over here that we are trying to make the change. Okay, so that does it does satisfy positive single choice principle. Satisfies single choice principle. So now that's why the conclusion is, if the visitor pattern is adopted, which should be open? Well, the answer is the operation part. Okay, hopefully that drew a very clear, also like a review about the visitor pattern. It should really be clear about what's the prerequisite for adopting the visitor pattern. Okay, I think that's about the end of the visitor lecture. Okay.